All right, last time we talked about more pigeonhole principle and continued our discussion of counting with permutations and combinations. And today we will talk more about counting with binomial coefficients and generalized permutations and combinations. So basically, just more techniques for counting. So let's start with binomial coefficients. So recall that what is a binomial coefficient? We write it in this notation, so parentheses and k, and we say and choose k because it is equal to combinations of k elements from a set of n elements. And we saw last time that there's a formula for this, which is n factorial divided by k factorial times n minus k factorial. So this is the definition of a binomial coefficient. And why does it have this name? Let's explain that. Let's get right into the binomial theorem. So the answer, I guess, is that they are called binomial coefficients because they are the coefficients when you expand a binomial. So what that means is if you have something like x plus y to the power n, it basically tells you what the expansion of this power of a binomial is. So binomial, of course, just means something with two terms like x plus y. So the claim is that x plus y to the n is equal to the sum of basically these coefficients. So sum from I equals 0 to n of x to the n minus I, y to the I, and the coefficient is n choose I. So just to write out some of these terms, this is n choose 0 times x to the n, y to the 0, plus n choose 1 times x to the n minus 1, y to the 1, up to n choose n, x to the 0, y to the n. So let's prove this. And the proof is essentially going to be another combinatorial proof. We are going to prove this by interpreting these coefficients as choosing I elements from a set of n. So let me start by sort of expanding a little bit this x plus y to the n, writing it as x plus y, just as a, writing it out the product. Where we have n factors in this list, right? So what do we do when we expand this, when we FOIL this out? Let's think about what this process means. When we expand this out, we're essentially, from each term, we are either taking an x or a y from this term. And from this term, we are taking either an x or a y, and so on. And this last term, we can either take the x or take the y. So what I mean by this is, just to say it again, each term in the expansion is formed by choosing, or let me say by taking, I want to reserve the word choose for when I'm talking about and choose I, by taking either x or y from each, from each binomial. So let's think about what the coefficient of x to the n minus I, y to the I is in this expansion. It is the number of times x to the I times y to the I appears when we expand it all out. And from this interpretation, it's the number of ways of choosing n minus I terms to take the x from, and I terms to take the y from. And once we have interpreted it like this, we can see that what we're doing is essentially considering these n factors as n different things, and we're choosing a subset of I, or equivalently a subset of n minus I. And that's determining whether we take the x or the y from each factor. So this is equal to n choose I. And that is the proof. So this is why they are called binomial coefficients, because they occur as the coefficients when you expand a binomial. But they also, as we talked about yesterday and as we just used in this proof, they also are counting the number of ways to choose a k-element subset of an n-element set. So you can start to see that they are very versatile. They have many different interpretations. And being able to use all of these interpretations and switch back and forth between them will allow you to do very interesting things. So now I want to give a little identity that comes from the binomial theorem. I believe I set a practice problem to give a combinatorial proof of this. So maybe you have already done that. Maybe you are already familiar. But here is another way of doing it from the binomial theorem. So the claim is that if we add up all the binomial coefficients from k equals 0 to n, with n fixed, this is equal to 2 to the n. And there's a very, very slick proof of this from the binomial theorem. So let me pull that back up onto the screen. And the proof is just that 2 to the n is equal to 1 plus 1 to the n. And when we expand this out using the binomial theorem, I should say this one, then what we get is the sum from k equals 0 to n. I guess I switched from using I to using k, but no difference. N choose k times x to the n minus k, y to the k, which is 1 to n minus k, 1 to k. This, of course, is just equal to the thing that we wanted on the left-hand side. So that completes the proof. And there are many different variations on identities that you can find like this. I mean, you can basically plug in whatever you want in these two slots and get a different identity out of it. So be on the lookout for those.